In last class, we learned that potential due to a point charge is 1 by 4 pi epsilon 0 q divided by r. Okay. And in last chapter, we learned that electric field is equal to 1 by 4 pi epsilon 0 q divided by r square. Okay. So let's see if we have a positive q and a positive q. Okay. What will be the field at the center? At the center, we keep a 1 coulomb test charge. Plus q will repel, plus q will repel. Okay. This is due to first one. This is due to second one. And you will feel that the field at the center is 0. This is the same if you are placing one minus and another also minus. At the center, what will happen? Field due to the first one will be attracting, second one will be attracting. Here also, the net field at the center will go to 0. But what if both the charges, one is plus q and one is minus q? So this is actually our dipole. So at the center, what will happen is, if you place a 1 coulomb, this will be repelled by first charge and attracted by the second charge. And we will say that your electric field is double. But this happens only if the distance remains the same and the magnitude of the charge is the same. What if the magnitude is different? For example, if I am giving, like, for example, I will take the first charge as maybe 5 into 10 power minus 8, okay, separated from a 20 into 10 raised to minus 8, okay, a 5 into 10 raised to minus 8 and 20 into 10 raised to minus 8. We will say that let it be at a distance of 2 meters. Okay. Definitely, as the charges magnitude are different, it will not be exactly at the center. Okay. So let's see that the field, let it be at a distance of x. At any point P, let the field be 0. So we will see that field due to the first charge, okay, that is 5 into 10 power minus 8, should be equal to field due to 20 into 10 raised to minus 8, because field is a vector quantity. So direction matters. So we cannot simply add and write it as 0. Okay. So we have 1 by 4 pi epsilon 0 5 10 power minus 8 divided by, first is x square. This will be equal to 1 by 4 pi epsilon 0 20 into 10 raised to minus 8 divided by 2 minus x the whole square. Okay. So we can cancel 1 by 4 pi, 1 by 4 pi, 8 power minus, and 5 will go 4 times. So we'll get 1 by x square is equal to 4 divided by 2 minus x the whole square. Rather than going to the quadratic form, you can take the square root on both the sides. When we take, we will get 1 by x is equal to 2 divided by 2 minus x. So 2 minus x is equal to 2x, or 3x is equal to 2. So what is the value of x? X will be 2 by 3 meter. From where? From the first charge. That means 2 by 3 meter from the first charge. At this point P, the field will go to 0. But what if it is potential? See children, if it is potential, for example, I'm keeping 3 into 10 power minus 8, okay, separated from minus 2 into 10 raised to minus 8, okay, coulomb. The distance between them is taken as 15 centimeter. 15 centimeter. This is the textbook sum. 16 centimeter is your NCRT in text, the chapter end also. So we assume that let it be at a point P distant x. Okay, so we need to find what is the value of x. In case of potential potential due to the first charge plus the potential due to the second should be equal to 0 because potential is a scalar quantity. So we will write 1 by 4 pi epsilon 0 3 10 power minus 8 divided by x. Don't put x square because it is potential. Is equal to, plus 1 by 4 pi epsilon 0 minus 2 into 10 raised to minus 8 divided by 15 minus x. This should go to 0. So if two quantities when added go to 0, it means you can bring it to the other side. So this will become 1 by 4 pi epsilon 0 3 into 10 power minus 8 by x is equal to 1 by 4 pi epsilon 0 minus will become plus 10 raised to minus 8 divided by 15 minus x. So as usual, 1 by 4 pi 10 raised to minus. So 3 by x will become equal to 2 divided by 15 minus x. That is 3 into 15, 45 minus 3x is equal to 2x. That means 5x is equal to 45. Therefore, x is equal to 9 centimeter. That means from 9 centimeter from the first charge, at P, the potential will go to 0. So this is the first part of questions you should be able to answer. The next concept we learn is that of equipotential surface. Equipotential surface. Okay. As the word suggests, equipotential means equal potential throughout. Equi means equal and potential means the potential at the surface. If I'm taking a charge Q, suppose if I assume a sphere around it with a radius R. Okay, so we can see that the potential at this point V is equal to 1 by 4 pi epsilon 0 Q divided by R. If you find the potential here, that is also 1 by 4 pi epsilon 0 Q divided by R. That means charge is not changing, radius is not changing. Okay, so the surface throughout which, okay, surface throughout which the potential remains constant. Throughout which the potential remains constant. The potential remains constant. This is what we call it as an equipotential surface. Okay, equipotential surface. So, what will be the work done to move a charge on an equipotential surface? We know that work done is equal to potential difference. And what is the potential difference in an equipotential surface? It is 0. Because potential difference is 0. Everywhere potential is same. So always remember work done to move any charge. They will give you any value of charge, 500 microcoulomb, 600 nanocoulomb, whatever be the charge, the work done to move a charge along an equipotential surface will be always 0 because there is no potential difference on an equipotential surface. Now, when you are putting a charge Q, okay, if I am putting a charge Q anywhere, you can see that the electric field lines are always emerging from it. Okay, all the time the electric field will be emerging from it. Like all the field lines will be emerging from the charge if it is plus Q. Okay. Now, when we are drawing an equipotential surface for this point charge, okay, for the point charge, if I am drawing an equipotential surface, you will see that the electric field lines are normal to the surface. That is, it will become 90 degree. Now, the reason for that is, we already know that the work done is 0. But what is the expression for work done? force times displacement. And what is force? QE into displacement. Now, we know that this charge, you take it as unit charge, then it will be E into displacement ds into, actually it is F dot ds. So this will give us F ds cos theta. Now this will be 0. That means if work is to be 0, electric field cannot be 0, displacement cannot be 0, then the only option is cos theta should go to 0. And cos theta is 0 only for 90 degree. And that's how we write that all the electric field lines are always normal to the equipotential surface. Okay. Now let's see what is the relation connecting electric field and potential. For that, we take two equipotential surfaces. Two equipotential surfaces we take, okay, and we see that this is your equipotential surface A, this is B. A is having a potential of V volt and B is having V plus dV. That means we are going to move a charge from A to B through a distance of dl, and that's the direction of the electric field, and we are moving it against the potential. That means here the potential is more, here the potential is less. So how do we do that? We write the expression for work done as work done is equal to force into displacement. That will become E into dl, because force means electric field. What is the next expression for work done? Change in potential. That means V minus V plus dV. We are moving it from V to V plus dV. So you will get this as minus dV. So what is EDL? EDL will become minus dV, or what is E? Minus dV by dl. That means negative gradient of electric potential will give us electric field. Okay. The next concept is, like electric field, if we are having multiple charges, Q1, Q2, and Q3. If there are multiple charges, then the total potential at any point P is given by the sum of the individual potential. And that is called superposition principle. So what is the total potential at P? The total potential at P will be equal to 1 by 4 pi epsilon 0 Q1 divided by R1P plus 1 by 4 pi epsilon 0 Q2 divided by R2P plus 1 by 4 pi epsilon 0 Q3 divided by R3P. This is for potential due to multiple charges. Okay. But if it is a system, that means potential due to a system of charges. It can be a system to make it into a triangle or make it into a rectangle or square. Anything can be asked. Okay. The distance between them is R12, R23, and R13. In this case, how we will find the work done? Work done is the potential energy. So this is equal to 1 by 4 pi epsilon 0, first two charges, Q1, Q2, divided by distance between them is R12, plus 1 by 4 pi epsilon 0, next two charges, Q2, Q3, divided by R23, plus 1 by 4 pi epsilon 0, Q1, Q3, divided by R13. So this is the total energy required to associate. Okay, this is the total energy to associate. So how we will find the energy to dissociate? Dissociation energy is negative of what is required to associate these charges. So this is one of the most important concepts. The total work done to associate a system will be equal to the negative of the total to dissociate it. So this is the total content for this week.